speaker for today is Dr. Hajime Ito. He is a distinguished professor in the Division of Applied Chemistry, Faculty of Engineering at Hokkaido University, Japan. He earned his PhD from Kyoto University under the mentorship of Professor Yoshihiko Ito. Following academic appointments at Tsukuba University and the Institute for Molecular Science, he conducted research at the Scripps Research Institute with Professor Kim D. Janda. He joined Hokkaido University in 2002, becoming a full professor in 2010 and vice director of the WPI ICREDD in 2018. Professor Ito has led major national research projects including JST, PRESTO, JSPS First, and JST CREST. His contributions to synthetic organic chemistry have been recognized with numerous awards, including the Chemical Society of Japan Award in 2024 and SSOCG Fujifilm Award in 2017, and multiple Hokkaido University President's Award. Thank you so much, Professor Ito, to join us here today, and the stage is all yours now.
Okay, thank you very much. Thank you very much for kind introduction, Neha. So I'm very happy to be here, and I'm very happy to share all of you with this moment. So I'm very happy to share my recent research. Okay, can I?
Yeah, please share your slides.
Yeah, slides. Okay, can you see this?
Yes, we are good to go.
Yeah, okay. So I will talk about mechanochemistry for that can revolutionize organic synthesis. So first of all, I would like to show this slide for introducing our university. So our university was established in 1876 as Sapporo Agricultural College. With some philosophy inspired by Dr. William S. Clark. He was first president of our university. His very famous word is "boys be ambitious." But this seems to be a little bit old because now we need to say that boys and girls be ambitious. And our city was situated in our university is situated in Sapporo, Hokkaido, and very famous for some organic chemistry and environmental science and material science researches. And we have two Nobel laureates. First one is Professor Suzuki, who is very famous for founding Suzuki coupling. And the second one is Benjamin List, who is also renowned as some research for organic some catalysts. Both of them are very important person for revolutionizing organic chemistry. And I would like to show say something about some ICRET. That is a very special institute founded in Hokkaido University. The aim of this institute is achieving the fusion research among organic chemistry, computational chemistry, and information science. And by showing this map, I would like to show some maybe location of our city and our university. And Sapporo is the most northerly large city in Asia. And we have a lot of snow in the winter time. This picture is a very typical screenshot of our campus. This is another one. And in the summertime, our campus was become very green and very beautiful. And this is a statue of a very important person whose name is Dr. Clark. And he's some first president in our university. And unfortunately, in the winter time, he can be covered by snow like this, and he cannot see anything. So it's very good idea to install Professor Suzuki's statue inside our building. Otherwise, our some Suzuki's statue can be covered by snow, as shown here. So this is our team for mechanochemistry, and they are very very nice students and researchers, and their enthusiasm and dedication make our all achievement possible. I appreciate them very much. This slide shows my very early research career. results of maybe research work on at our research career. I started my research career at Hokkaido University in collaboration with Professor Akira Suzuki, who is very famous for finding some so-called Hosomi Sakura reactions. And in his laboratory, as an assistant professor, I started my research career. And fortunately, I found that the first example for carbocation evaluation. This is a very important reaction. And usually some boron group can be used as electrophiles. But in this reaction, boron group can be act as a nucleophilic reagents in the presence of copper catalyst. And this reaction is very useful for construction of organoboron compounds, especially for optically active organoboron compounds by combining chiral catalysts. More recently, we also developed new ligand for these carbocation reactions. These are representative example for organoboron synthesis we published last 10 years. So during our study for developing new reactions for organic synthesis, we found that this gold complex can show some very interesting optical properties. We try to make some new catalyst. We first try to make a new catalyst by using these compounds, but unfortunately, this compound is very stable, and we cannot find any catalytic activity, any reactions by using this compound. This compound is very stable. We can keep this compound in the bench for 2 or 3 months without any some chemical degradations. Instead of catalytic activity, we found that very interesting. This compound can show the very interesting photoluminescence properties. These compounds can be seen as a white powder, as shown here. But under the UV light illumination, these compounds can show very weak luminescence, phosphorescence. Interestingly, this blue color can be converted to the yellow color by agitation of a spatula like this. So you can see this blue color can be converted to yellow color. And by using PESU, you can see more drastic color change from blue to yellow. This color change, we found that this color change is based on the crystal structure change of microcrystalline blue emissive state to some yellow emissive amorphous state, as shown here. So more interesting is this yellow color can be reverted to the original blue color by addition of solvent. In this case, we use dichromethane. As you can see, this yellow color can be reverted to the original blue color. This is very similar to just a recrystallization from amorphous state to microcrystalline blue luminescent state. And after the evaporation of solvent, you can see this color change again and again without any color degradation. We check some at least 20 times. We can repeat this blue color to yellow, yellow color to blue changes like this. So after these findings, we tried to make many different mechanosensitive compounds based on the gold isocyanide structures. So unfortunately, we also found many examples for mechano-responsive color-changing materials in collaboration with Professor Seki and Professor Mingu Jin. So this is another example. So we call this example as some molecular domino. So this is a single crystal of the compound. And this is a microscope image and under the UV light illuminations. So my students put some mechanical stress on these crystals by using a very tiny metal pin. And you can see a new crystal phase can be generated that is starting from point mechanical stress was applied. You can see this crystal change was also accompanied by color change, blue shifted color change. Because of the some camera is not so good, you can see some blue color after the mechanical phase change. But this is a single crystal to single crystal color changes. Single crystal to single crystal structure changes. This is a crystal structure, and this structure is some just before some phase change induced by mechanical stress. As you can see, all molecule was connected through orophilic interactions, constructing six hexameric helical-like molecular structures. This is a crystal structure after the mechanical stimulations. You see all molecule was crystallized as a layer by layer structures. And in these structures, orophilic interaction disappears. Instead of orophilic interactions, CH pi interaction was generated in the new crystal phase. This structure changes also corresponds to the color change green to blue shifted blue, green color to blue shifted luminescence. So what inspired me from the study of mechanochromism was that organic solid can change more easily than we expected. Our organic chemists have a very strong image that molecular crystal or solid materials should not react easily or some should not change their structures. But I have some long experience for developing new reactions in solutions. And more recent, after last 15 years, we have experience about new materials development in the solid state. I thought I thought that we can combine these two concepts and to experience and the knowledge to develop new reactions in solid state. This is the motivation of our motivation for researching mechanochemical organic synthesis. And this is a conceptual exploration for mechanochemical organic synthesis. If we want to make a new reactions by just reacting two solid materials, but mixing efficiency is not so good, so usually we can only find a very small amount of desired product on the surface of these crystals. Instead of just mixing molecular organic crystals, we organic chemists use some large amount of organic solvent to dissolve these compounds to react freely in some organic solvent. But recently, some mechanochemistry people can find that by using ball milling machine, we can conduct some organic reactions with solid materials in the presence of small amount of organic solvent or in the absence of small organic solvent. And almost 6 years ago, I invite Dr. Koji Kubota to collaborate to develop for development of new mechanochemical organic reactions. So fortunately, we found many new things, and I think we found several practical methods for some organic synthesis by using ball milling machine. This is what I'm talking today. So this is a ball milling machine, and we put some balls and substrates into the jar, and we put that jar to some organic ball milling machine like this. So, and we close some cover of this machine, and the reaction can be started by just pushing starting button. And the vibration of this machine is typically 30 Hz, and not so very super high, but this is enough for promoting organic reactions. And this is, I am not some first person for organic synthesis in mechanochemical reaction conditions. There are already some pioneers, many already books and reviews already reported. But we started to, some 6 years ago, we focus on some mechanochemistry as a we try to such a maybe classical mechanochemistry more practical by finding some good reaction conditions that can more efficient and more useful compared to some conventional solution-based reactions. We first focus on the cross-coupling reaction because cross-coupling is very important for organic synthesis. This is some example for reactions for drug discovery. And more than 30% of reactions using drug discovery is cross-coupling reactions, showing some importance of cross-coupling in organic synthesis. So we first tested the reaction between liquid starting materials and solid starting materials. But this reaction is expectedly works very well by using ball milling. However, if you want to make a reaction between two solid materials, some reaction did not proceed very well. And because of the decomposition of palladium catalyst, only 80% of product yield was found. Starting point of our study is to find out some very good reaction conditions or good additives to improve this reactivity. So Dr. Koji Kubota is a very capable person. He quickly found that some addition of 1,5-COD improved this reaction very much, and by stabilizing palladium some catalytic species. And these are example for cross-coupling for using this palladium catalyst, including 1,5-COD. And we found that this reaction condition is very general. And we also try to find a good reaction conditions for sweet coupling also. And 2000, already Peters and Alexason first example already published the first example for cross-coupling in some bottoming reaction conditions. But another people also reported several examples. But honestly speaking, the reaction not so very so far, so not so very general and not so useful for some many substrates. And then we decided to find a very good reaction conditions. So already almost same time, Professor Su in China, Professor Brown in UK already reported, also reported some palladium catalyzed cross-coupling reactions in the bottoming reaction conditions. But they already report their example just some liquid materials. So, but our sweet cross-coupling reaction more focusing on some solid materials. And we also found that some addition of the 1,5-COD can improve this reactivity very much. And these are examples. And I would like to show this slide to convince you some mechanochemistry is more efficient compared to some conventional solution phase reactions. And this reaction we use some anthranil bromo substrates because reactivity of this compound is not so very high. So in this case, we need to use a large amount of solvent. In this case, we use 160 milliliter of dioxin. Of course, this dioxin should be dried and degassed, and not that process is required. And we should use a very huge, some glasswares. And this reaction should be conducted some argon or nitrogen atmosphere. This glassware also needs condensers because we heating up these reactions. Of course, some heating up some oil baths also required. But even these reaction conditions, we only found that some reactivity is not so very nice. And after the 100 degrees Celsius reaction temperature and 24 reaction hours, but only 50% of product was found. But our mechanochemical reaction conditions, we just only use a jar. Okay, I'd like to show a pointer here. So just we use this jar, and we just put some ball and substrate inside jar under the air conditions. But we conducted this reaction at room temperature, and reaction time is just 1.5 hours. And even this reaction condition, we were able to get some desired product very high yield compared to some conventional reaction conditions. So this slide clearly showed that our mechanochemistry reaction conditions is much efficient and much more easy to do. And many people ask to some scaling up conditions. So this is not pure scaling up. We just some larger ball milling with that enables some 100-gram scales. And we repeated this 100-gram scales 10 times to achieve this scaling up reaction. 1 kilogram cross-coupling product can be synthesized by some ball milling reaction conditions. So this slide shows you why some addition of the 1,4-COD improve this reaction. So this is a TEM image after some reactions in the absence of 1,5-COD. You see palladium can be aggregated each other to form some palladium nanoparticle, so-called palladium black. This palladium black has a very low activity for cross-coupling reactions. So in the solid state NMR, we see some free Dave host was generated. This means that palladium phosphine catalyst was decomposed under the ball milling reaction conditions. This is some TEM image in the presence of 1,5-COD, and the palladium nanoparticle can be suppressed, and less amount of palladium black was found in the reaction conditions, results. This is a solid state NMR also show that palladium zero species coordinated by host pin ligand and 1,5-COD also present in the some reaction mixtures. And this clearly shows that addition of 1,5-COD stabilizes palladium zero resting species in the cross-coupling reaction, because palladium zero species can be aggregated because of some high reaction concentrations in the ball milling reaction condition. Without 1,5-COD, palladium zero decomposed to palladium zero more easily. And we established a very nice reaction conditions. So we try to make a new directions for cross-coupling reactions for insoluble compound. Insolubility is a very big problem in organic synthesis because many organic reactions highly depending on the solution reactions. And if you want to make a new reaction of insoluble substrates, only method we can do is just a long reaction time and a large amount of solvent with high boiling points at high temperature. But this is sometimes okay, but sometimes not so very efficient. So we thought that for the ball milling reaction conditions, we don't need to dissolve all compounds into some organic solvent. So we thought that we can have some possibility to conduct cross-coupling reactions of insoluble materials by taking advantage of this ball milling reaction conditions. So we first try to some cross-coupling of these substrates because some solubility of this substrate is comparable to carbon-60. If we can conduct cross-coupling we achieve this cross-coupling of these compounds. This can be a very good maybe a good presentation for some insoluble cross-coupling reaction of insoluble materials in ball milling reactions. But at the room temperature, we cannot find any good yield of the products after the long reaction time. We are so disappointing, but we thought that some cross-coupling reaction usually requires some little bit high temperature. No, room temperature is, in any cases, not so very good results. So we thought that, however, some ball milling machine at that time, some company who make some ball milling machine has no very good option to heating up some jar. So because usually some ball milling machine is usually some sold for some making some powder from solid materials. Making powder, low temperature is more favorable, and high temperature is not so very good for making good powder. So that's because the company for ball milling machine had no options for heating up. So we try to make we try to heating up some ball milling jar by using this a heater, but some connection was not so very good. Some easily break after the reactions. So we also tested a lamp and a hair dryer, but hair dryer is not so very powerful for heating up ball milling jar. So finally, we found that some use of, not we, I found that some temperature controllable heat gun in the some Amazon market store. So this is very useful. And but just changing some air temperature, we can control some inside temperature of the jar. So in the typical case, if we set some air temperature 250 degrees Celsius, inside temperature should be 120 20 degrees Celsius. This temperature can be checked by some thermographic camera as shown here. So some heating up the jar is very powerful for ball milling cross coupling. So at the room temperature, no reaction after the 60 minutes. And in toluene, higher temperature, this is a solution phase reaction, 120 degrees Celsius. So reactivity is not so very nice. After the 60 minutes, only 20 or 30% of the yield is found. But after the 1 day, because of the decomposition of the palladium catalyst, we don't find a very good yield even after the 1 day's reactions. But some ball milling at higher temperature, very powerful. So only 5 minutes was required to cross couple of this insoluble already highlighted boric acid. So we tested other substrates. This substrate is some very similar in regarding some their solubility for some carbon 60, but this works very nice. So only 5 minutes is required for ball milling reaction conditions. So this compound is less soluble compared to the carbon 60, 10 times less soluble, but cross coupling works very nice. And this compound is more less soluble compared to carbon 60. This is a pigment, and almost no. This is so insoluble in organic solvent. But some ball milling reaction can change these compounds to the soluble materials. So this is we use a tertiary butyl group for coupling partners. This whole tertiary butyl group can this compound soluble, and otherwise we cannot check this reactivity. So starting material is insoluble, but product is soluble in our ball milling reaction studies. Interestingly, these compounds show very nice luminescence in the some solution state. So we believe that this cross coupling is a very nice way to find a new to development new functional materials starting from a very old, very common pigment compound. So we also check some reactivity of other insoluble materials, and we found that even 100 or 100 times less soluble compared to carbon 60, such compounds also can be useful for cross-coupling reaction in the ball milling reactions. This, of course, this is this is impossible in some previous solution phase reaction systems. So this paper was fortunately selected as a cover page of JACS journals. And I asked the company who make these illustrations to put some my lovely heat gun inside some these pictures. So this heat gun can be a very small compared to the molecular size. I think this heat gun can be, you can say, some nano size heat guns. in these pictures. We also reported several other cross-coupling reactions in the ball-milling reactions. Some first one is some monoselective cross-coupling by taking advantage reactivity difference of starting materials and some mono cross-coupling products. And second one is some catalyst improvement by introducing polymer side chains to some ligand. This side chain can make some polymeric fluid phase that enhance the reactivity of this paradigm catalyst in the polymeric reaction conditions. So some maybe for cross-coupling reactions, some major role of ball milling mixing is just some maybe high mixing efficiencies. But we try to make some new another we try to find another possibility for ball milling reaction conditions by using mechanical force generated in some ball mill jar. So first example, I would like to introduce you some activation of metals. We try to generate Grignard reagent in the ball milling reaction conditions. Of course, the Grignard reagent is a very important, very famous reaction. It's a very famous reagent in organic synthesis. But we believe that this Grignard reagent should be synthesized in the solutions by just mixing organic halide and metallic magnesium. So that we try to make some Grignard reagents by using ball millings. So already several pioneers already reported example for trial for Grignard reagent formation by using ball milling. But some Harhold reported and Bilke already reported only protonation was found, or homocoupling reactions, or some maybe linear reagent did not work very well in the compared to some solution phase linear reagents. But we found that addition of 2 or 3 equivalent of THF can improve this reactivity very much. With sometimes we also heating up this reaction jars. So we found that linear reagents can be synthesized in the ball milling reactions conditions very efficiently. This is a picture without THF additives. This is just a mixture of magnesium powder and substrates. This is a picture for some in the presence of THF. You can see some peanuts butter like THF can be generated in the ball mill. This is the first example for Grignard reagent formation by using ball mill reaction conditions. So these reactivity of this new type of Grignard reagent is very similar to some conventional conventional Grignard reagent synthesized in the THF or ACS solutions. So we also, and surprisingly, this Grignard reagent is relatively stable compared to some solution state. Grignard reagent synthesized by conventional solution phase. So for reactions, we just after the we first synthesized Grignard reagent by ball milling, and we opened the jar, and we added aldehyde, and and after the closing some jar, we continue some reactions. So we open the jar just maybe in a usual case, we just open this jar only less than 1 minute. But we try to keep this opening 10 minutes or 30 minutes or 60 minutes. And we observe some reaction, some products. But surprisingly, after the 10 minutes opening, this Grignard reagent still alive. Of course, some product yield was decreased, but 40% of product can be observed. This means that in some opening time, surface of this peanut butter like linear reagents can be decomposed, but inside is not very stable. This result clearly show that linear reagents prepared by some Boltzmann reaction conditions is maybe little bit relatively stable compared to some solutions. Linear reagents prepared in the solution phase reaction conditions. We also check the structure of these compounds by comparing some linear reagents prepared by conventional method by using Nexus. So this clearly show that some structures very similar each other. We also try to find out possible structure of new linear reagent in collaboration with Professor Maeda and Professor Jan by using AFIR and DFT method. The AFIR is a very special technique that can determine every possible intermediate transition state automatically. So they finally found that this cubic-like structure is the most stable and for some linear reagents prepared by THA, some Boltzmann reaction conditions. Interestingly, coordination of THF is very important to stabilize this new linear reagent. So next, we try to make a organocalcium compound. So calcium is a same group to magnesium. And but however, because of calcium is very stable metals, some synthesis of organocalcium reagents not so very easy compared to some linear reagents. For linear reagent synthesis, you can just mix some magnesium and alkyl halide in some solution or ball minute. But calcium is very stable compared to some linear magnesium metals. Just mixing calcium and organic halide did not produce some calcium reagents. Some in the literature, activation of calcium is required, such as Leake method or sublimations. Or some you can synthesize just some transmetallation of, for example, alkyl lithium and calcium salts. And however, if you make some oral calcium reagents, because of electronegativity of calcium is much lower than magnesium, you can synthesize very high reactivity. Some organometallic compounds with very high reactivity. So we tested the reaction of calcium and organic halide in the solutions, but as already many literature shown, so we cannot find any good results in the just by mixing calcium and organic halide in solutions. But in the Boltzmann reaction conditions, some calcium can react with organic halide very quickly, so to form some organic calcium reagents. And this is a picture before some ball milling. This is a picture just after the ball milling. So by taking advantage this reaction method, we found that organocalcium reagent was easily synthesized by just using ball milling reaction conditions. So, okay, I would like to skip. And more recently, we synthesized organolithium reagents by using ball milling reactions. So even various lithium reagents like even tertiary lithium also synthesized in Boltzmann reaction conditions. So we also find that some batch reduction can be conducted in the Boltzmann reactions. So batch reduction is very important for partial reduction of aromatic compounds, but some in practice, so batch reduction is not so very easy to do because we need some large amount of liquid ammonia for some conducting linear reagents. But we try to use Boltzmann reaction conditions for some batch reductions. And we found that some batch reduction can be conducted very easily by just putting some lithium metals inside jar and substrates and shaking this volume jar. And only the surprising thing is only 1 minute was required to finish these reactions. So this is a picture just after the some reaction. This is a picture just after the quenching. And then we check some reactivity of this new batch reduction, almost same to some conventional batch reduction. This is a table of products. This is also. So we also conducted some test tube reactions by using same additives and substrates and lithium. But after the 5 minutes, almost all lithium remained. Even after 2 hours, some messy reduction can be found, but all lithium still remained. This means that, of course, our reaction can finish only 1 minute. This shows that mechanical agitation on the surface of lithium in the presence of substrate is very important for these high-speed reactions. So, Professor, other people also reported similar results. Some Elri Liu and Professor Kananovich also reported similar large reactions. So I think some by activation of metal surface, I believe that we can open the new some way for synthesizing organometallic compounds. This is, I think, this is a very good direction for mechanochemistry. So because of the time limitation, I would like to skip some polymer activations. So, and I would like to show the final story about this talk. So by showing these pictures. So piezoelectric material research. Well, piezoelectric material is very important for our daily life. This banner also have some piezoelectric chip here. So by adding some mechanical agitations, this chip can generate electricity to like this sparks. So piezoelectric material can change mechanical stress to electricity and electricity to some maybe mechanical vibration or something. So piezoelectric materials is was used for speaker or mics by taking advantage these properties. So this is barium titanate, very representative piezoelectric materials, very cheap and very stable and very less toxic. This is a very important compound in organic people, but no organic people wanted to use this catalyst, these materials for the catalyst of organic synthesis. And one day I got a very crazy idea to use these materials for some maybe alternative for photoredox reactions. So in the photoredox reactions, photocatalyst excited by light to generate electricity. And this electricity can make some electrons. And after some one electron transfer induced reactions, this catalyst also promote the next reaction. So one day I got a very crazy idea that piezoelectric materials also can generate electricity by Bornholm reaction conditions. And I thought that this electron can also promote some redox type reactions. This is a cartoon-like explanations. We just mix barium titanate and organic material, organic compounds, and under some Bornholm reaction conditions, agitation, mechanical agitation can generate electricity or Hall to promote these reactions. And we also we employ some reactions that was already reported as a photoredox reactions. And I asked them to test these reactions using some diazoxide salt and furan in the presence of barium titanate in the core meal. And in the first shot, they found very promising results. And higher frequency, they found very higher reaction products. So without barium titanate, only ball mill cannot show any good reactivity. And aluminum oxide, titanium oxide, that has no piezoelectricity shows no reactions. So barium titanate with in solution by to gently agitating these materials, but this has no reactions. So these are results of ball milling reaction conditions. And this is a result of cross-coupling between diazonium salt and some heteroaromatic compound. This tables can show barium titanate is a very good catalyst for this cross-coupling. This is a boration reaction results. Also, boration also occurred in some barium titanate catalysts. I asked him to make a plastic bag, including barium titanate and substrates, and I asked him to some punching this barium titanate bag. And this is really crazy some movie, so nobody can understand what we are doing here. But we found some boron compounds can be generated by reaction in the presence of barium titanate after the hammering 200 times. This is one of the most craziest reaction conditions. But fortunately, we conducted this barium titanate catalyzed reactions by just hammering. So we also check some barium titanate is more general for organic synthesis by by showing trifluoromethylations. Okay, this has mistakes. This is no trifluoromethyl here. So or cross coupling between some bromide amines. Okay, I also skip some amines partners. Amines 2A, and this is nickel bromide was of course reduced by barium titanate to promote these reactions. So this is a take-home message for Born-Milling reactions. So, but I would like to skip because of the time limitations. This is the final slide. So very older time, human found that some mechanical agitation can be very useful for making a tools, making our civilizations. And finally, a human found that these tools also very finally we found that so like a spaceship, a human can make a spaceship finally. This is taken from some very famous movie 2001 Space Odyssey. But some organic chemistry is very behind compared to some normal human. Only very recently we found that mechanical punching is very important for some organic synthesis. So I believe that mechanochemistry is a very good tools for finding some innovative reaction process in the future. I hope mechanochemistry has a very nice, very big possibility for making revolutionizing organic synthesis more greener, more efficient, and more useful in our some human life. So finally, I would like to show some my appreciation to my colleagues and my funding from our government. Okay, thank you very much for your kind attention. Thank you very much.